Today I'm gonna discuss something about the atomic structure, which might influences the material's mechanical property, electrical property, chemical property, and physical property, and so on. So the structures on various levels or length scales can profoundly influence the material's property, behavior, and applications. And basically there are five main levels of a structure: atomic structure or atomic arrangement, nanostructure, microstructure, and the macrostructure. Okay, so basically atomic structure might influences the material's electronic properties or optical properties or the chemical property and so on. Okay, and the atomic arrangement might have some affection about the mechanical property, and also the microstructure or the nanostructure provides some like such as the surface property. Okay, the surface behavior with different structures. Okay, so I have some examples here. So what's this? It's the laser. So the laser spout with something like the dimple shape of the nano or microstructure. So that's the reason why the lasers can stick to the wall or can stick to the roofs due to the high surface area of its spout, right? So it can suck or stick, okay, vertically or on the roof and so on, due to the the micro or nano structure. Okay. So the issues to address includes what promotes bonding. Why these have these two materials have the strong bonding, while the other two has the weak bonding. Okay, what's the difference between the strong and weak? Okay, and what types of bondings are there, and what properties are inferred from the bonding? Okay, that's the issues we're gonna address on these topics. So let's have some review, some freshman chemistry or the high school chemistry. So the atoms includes electron, proton, and neutron, and the electron mass is 9.11 times 10 to minus 31 kilogram. Okay, so you guys have already knew this, right? An atomic number equals to number of protons in nucleus of the atom equals to number of electron of neutral species. So that's mean the balance of charge, right? And atomic mass units is known as the AMU equals to 1/12 mass of carbon 12. Okay, and the atomic weight is equal to the weight of 6.022 times 1023 molecules or atom. That's mean the weight per unit mole, right? The weight per unit mole. Okay, so the 1 AMU per atoms equals to 1 gram per mole. 1 gram per mole. It should be the high school chemistry we have already learned, right? Okay, so the valence electron determine all the following properties: chemical, electrical, thermal, optical. Okay, so I have a question: is what is valence electron? What is valence electron? Oh, it's very important. Well, it's very important for those physicists or chemists. Okay. So the valence electron is the outmost shell. It's the number of electrons located at the the most outer shell. And those valence electrons determine those properties: chemical, electrical, thermal, and optical properties. Okay. However, the mechanical property will not be influenced by those valence electrons. Okay, mechanical strength or the tensile stress, the yielding stress, or the toughness will not be, the valence electron will not affect those mechanical properties. Okay. Okay, so another important quantum mechanical principle stipulates that the energy of electron are quantized. That means the energy of electron are not continuous. Okay, it's not continuous. Thus, electron are permitted to have only specific value of energy. Okay, basically for our mechanical engineer or the material science engineer, maybe this quantum concept is not so important for us. However, it's important for those chemists and the physicists. Okay, we still need to have some ideas about these quantum mechanics principles. Okay, so the quantum jump, the electron gonna jump from the low energy level to higher energy level as absorbing the energy. Okay, some example. For example, some semiconductor, as you provided some energy, for example, heat, or the light, photon, or the voltage. So when you apply some external potential, external energy to those semiconductors, so it's become more conductive or not. It's a semiconductor. You have to think of it. So we have a semiconductor. I don't care about what it is. However, it's a semiconductor. And I apply some energy, external energy, such as heat and the voltage or the light or some photons. Its resistance, for example, its resistance is increase or decrease. Okay, so when we apply external energy to the semiconductors, its resistance will decrease, right? So that's mean we apply the external energy to excite the electron inside the semiconductor. It might jump to, it may leave its outer shell to become a free electron. Okay, become a free electron. And when the electron fall to the low energy level, that means the energy is emitted. Is emitted. So the emission of energy might induce the light or the heat. Okay, the light or heat. Okay, so the electron energy are associated with energy levels or states, and each electron has its own specific energy level. Okay. Okay. So let's look at the atomic models. So you guys already, I think, is not quite different. So we have the this atomic model. It's called the Bohr atomic model. So we have the nucleus at the center, and with different orbitals, and the electrons are located at different orbitals. Okay, at different orbitals. So the electron can be regarded as a wave or particle. So electron has two properties, wave-like or particulate properties. Okay, so the electron are in the orbital defined by a probability. So what's that mean? What's mean the probability? That's mean the probability to find electrons at that specific orbitals. Okay, so I'm going to introduce this later. And each orbital at the discrete energy level is not continuous, it's discrete energy level. So we can define the electron energy by quantum number. We can define the energy of electron by 4 quantum number. Okay, so if we have this 4 quantum number, okay, we might know where to find where is the highest probability to find the electron. Okay, if we know these 4 quantum numbers, maybe 3 for 3 quantum numbers. Okay, so this quantum number defined by the physicist. Okay, so let's see the 4 quantum numbers. N is the principal or the energy level shell, the principal quantum number. The destination is K, L, M, N, O. So the K equals to the first shell, the inner shell, the innermost shell. L equals to the second shell, okay? And I means the subshell or the secondary quantum number. Okay, so it defines the subshell within the principal quantum number. So okay, so for example, the K shell has the its subshell. The L shell has its own subshell. The M shell has its own subshell. Okay, and the subshell is defined by SPDF. Okay, SPDF. And the third quantum number is magnetic quantum number, or the third quantum number. Okay, the third quantum number. And the fourth is MS equals to spin quantum number. It's defined the spin orientation of electron. Spin orientation of electron is counterclockwise or clockwise, and so on. For example. So electrons occupy discrete energy level within the atom, right? And only 2 electrons may occupy the same level. Each electron's energy level is identified by 4 quantum number. Okay, so we have mentioned this from the previous slide. Okay, N is the principal quantum number. N equals to 1, 2, 3. And L is the secondary quantum number, or the subshell quantum number. L equals to 0, 1, down to N minus 1. And the third quantum number, ML, equals to 2L plus 1 for each L. L is the secondary quantum number, right? And the spin quantum number is MS equals half and minus half, so on. Okay, so let's look at the it's called the Pauli's expulsion principle. That states the no 2 electrons in one atom can have the same 4 quantum numbers. So that means no more than 2 electrons can occupy the same orbitals. Okay, so if the electron, one electron has the same quantum number, has the same 3 quantum, the first 3 quantum number, and the last one is called the spin quantum number. Its direction, its spin direction must be different. So that's we say no more than 2 electrons can occupy the same orbital. Okay, and 2 electrons in the same orbitals must has the opposite spins. Okay, if the first 3 quantum numbers are the same, and 2 electrons in the same orbital must have opposite spins. Okay. So let's look at the. I think the statement is quite abstract, right? So let's look like these figures. We have the atomic model like this. So nucleus. We have the shell, right? We have the shell. N equals to 1, 2, 3, K, L, M, and each shell has the has its own electron, and each principal quantum, each shell has its own subshell, I will introduce this later, has its own subshell. Okay, so this figure shows the energy level. Okay, the energy level. Okay, so as the n equals to 1, that's mean n equals to 1, n equals to 1 here. So n equals to 1, right? N equals to 1 right here. So n equals to 1 means k equals to 1, and its subshell is 1s. This one means n equals to 1. Okay, n equals to 1, and its subshell is s. Is s. Okay. I'm sorry. Okay, so when the principal quantum number n equals to 2, it has two subshells, S and P, right? So this 2 means the principal quantum number. Okay, n equals to 2, the second shell. Okay, and as n equals 2, it has two subshells, S and P. As n equals to 3, it has 3 different subshells, SPD. Okay, normal sign. So this number means the this number means the principal quantum number. Okay, means the principal quantum number. Okay, this means the principal quantum number. Okay, and this the secondary quantum number SP, SPD, and so on. Okay. So let's look at this. It's called the wave mechanical model. What's that mean? Wave and the mechanical. Well, we have mentioned before like this. The electrons are wave-like, and the particulate. So that's mean for the mechanical model. Our idea is that okay, we can find the electron at a specific orbital, just like this, right? So for example, I can find electron here, right? Just right here at this orbital. Okay. But for the wave model, we'll say the electron is not located at a specific place or orbital. Well, it's at a specific orbital, but the place is a probability. So you can see the electron. We'll find the electron cloud. It's a property. At this property, we properly to find the electron. Right. So you will see, for example, here. Okay, we'll find the electron right here. This is the nucleus right here, and this distance from the nucleus, right? So from the mechanical model, we'll see, okay, we'll find the electron right here. However, for the wave model, it's a probability. So we know, okay, maybe at this location, away from the nucleus, we have the highest probability to find the electron. You know what I'm saying? But it's not maybe we can find electron, but it has the highest probability to find the electron. Okay. Okay, so let's look at the quantum number. The quantum number. Okay, the quantum number. So every electron in your atom is characteristic by quantum number. That's what I already mentioned before, including the shape, size, and the special orientation of the electron's probability density. So if we know these quantum numbers, we know we can find the electron. We have the highest the probability to find the electron. Okay, so look this again. We have the K, right? The principal quantum number K, and the number is 1, n equals to 1, and it has one subshell. Okay, and its number of state is ml. It's the third quantum number equals to 1. Okay, and each subshell has 2 electrons. Okay, have 2 electrons. Therefore, per shell means the K shell has 2 electrons. Okay, the K shell has 2 electrons. As n equal to 1. So as n equals to 2, the shell destination is L. So it has the 3 subshell. It has 2 subshell, SP. Okay, SP. So its number of state is 1. One number of state has 2 electrons. That means in S shell, we'll fulfill the electron of the S subshell. We need 2 electrons. Okay, 2 electrons can fulfill in the S subshell. Okay, and for the P shell, its number of states are 3. Okay, 3, and each the electron of each number of states has 2 electrons, right? So for the P subshell, the maximum electrons are 6. So the 6 electrons can fulfill in the P subshell. Okay, so 2 plus 6 equals to 8. So for L shell, or for the principal quantum number equals to 2, the maximum electron is A electron, and so on. We have n equals to 3. The principal quantum number equals to 3. Its destination is M, so it has 3 subshell: SPD, SPD, SPD. Okay, SPD. Okay, so we have 1, 3, and 5 number of states. So we have the 2, 6, and 10 electrons per subshell. So for the M shell, totally there are 18 electron. Okay, 18 electron, and so on and so on. So yeah, so the principal quantum number equals to 4. The destination is N, so it has the 4 subshells, and totally has the 32 quantum numbers per shell. Okay, per shell. Okay, so that's why I mentioned here is that the Bohr energy levels separate into electron subshell, and the quantum number dictated the number of states within each subshell. And the shells are specified by a principal quantum number n, okay, which might take integral values beginning with unity. Sometimes the shells are designated by the letter K, L, M, and O, and so on, and n equals to 1, 2, 3, 4, and so on. Okay. Okay, and the quantum number is related to the distance of the electron from the nucleus, or its position. Okay, and its position. So I already mentioned before, right here, right here. Okay, so the quantum number is related to the distance. It's related to the distance, right? The distance. Okay, the distance from the quantum number, from the nucleus. Sorry, from the nucleus. Okay. Okay, so let's look at the second quantum number. The second quantum number, L, signifies the subshell, okay, which is denoted by a lowercase letter SPDF, and it's related to the shape. The shape, okay, it is related to the shape of the electron. Okay, the shape of the electron. Okay, and the number of this subshell is restricted by the principal quantum number. Okay, let's look at the figure below. So for the s orbital means k, for example, k, if k has the s orbital, right? That means n equals to 1. Okay, n equals to 1. And the s orbital, its shape is like sphere, it's like this. It's a sphere. That means, okay, right here is the nucleus, right? It's a nucleus here. And the s subshell is like sphere. That means inside the sphere, we can find 1 electron. Okay, inside this sphere, we can find 1 electron. Okay, the same thing. If n equals 2, so we have the p orbital, right? S and P. So the shape of the p orbital is like a dumbbell. Okay, it's like dumbbell like this. It's like this. So that means we can find the electron within this shape. Okay, within this shape, in this shape. Okay, you know what I'm saying? So we have the S shell, S orbital, it's a sphere, we can find the electron inside the S shell. So we can find inside this sphere. And for the p orbitals, we can find the electron inside the dumbbell shape. Okay, the dumbbell shape. So we can look at this for the s orbital, the subshell. It's the sphere. We can find the electron inside, and its third quantum number equals to 1. Only 1. That means we say this number of states, right? The first, second, and third quantum number. Okay, so the third quantum number defines the number of states. So we look at this figure shows S subshell ml equals to 1. Okay, equals to 1. That means only sphere. You can find the electron inside the sphere. So when you have the p orbitals, your third quantum number equals to 3. Okay, so that means we have 1, 2, 3. We have 3 number of states, 3 states. Okay, different direction of this dumbbell shape. We can find the electron here, inside here, 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 or here, right? For the d orbital, d subshell, its number of states equals to 5. That means we have the 5 number of states. So we can find the electron inside this yellow region. Okay, yellow region. And for the F subshell, right here, we have 7 number of states. 1, 2, 3, 4, 5, 6, 7. right? So we can find the electrons inside this green region. Okay, so that means this is the s orbital, this is the p orbital, is the d orbital, is the f. Okay, so you just need to have this basic concept for this course. Basically, it's for the engineer, okay, for the mechanical engineer or the materials engineers. So we just need to have some concept of this these quantum numbers. Okay, it's not the main subject we need to focus on. Okay, but you need some basic concept of this. Okay, so this already mentioned this. Okay, I already explained this, so you can read it by yourself. Okay, so let's look at this figure. It shows the quantum number and the energy. Okay, so we already mentioned the quantum number is related to the distance the distance of the orbital from the nucleus, right? So it's the s orbital is the close to the nucleus. N equals to 1, 2, 3, 4, 5, 6, right? So the n as n equals to 7, that means this the away from the nucleus. Okay, away from the nucleus. Okay, right. So for the n equals to 2, we have the 2 subshell S and P. For the n equals to 3, we have the 3 subshell SPD. For the 4, we have the SPDF. Okay, for the n equals to 5, we have SPDF. I'll say it's all the same after n higher than 4. Okay. So the electron structure of the atom will follow a principle. Okay, that means the electron will fielding. Okay, follow this principle. Okay, so the electron will fielding in 1s this direction from 1s, 2s, 2p, 3s, 3p, 4s, 3d, 4p, 4s, 4d, 4p, 6s, and the 4f, 5d, 6p, and 7s. Okay, this is the direction means the electron fielding, the priority that electron will fielding. Okay. Okay. So give you some example like this. So I already mentioned this before, right? The valence is the number of electrons in the atom that participate in bonding and chemical property. Okay, so usually valence electron is the number of electrons in outer s and p orbital. Usually, give you some example like this. For example, the magnesium, its electron configuration or electron structure is like this. Okay, it's like this. So the n equals to what? 3, right? Because 1, 2, and 3. Okay, 1, 2, 3. So what's its valence? What is the its outer shell? Outer shell. N equals to 3, right? The outer shell as n equals to 3. So its valence is it's 2, right? We have 2 valence electron. Know what I'm saying? Okay, for example, the second example is aluminum. N equals to 3, right? N equals to 3. N equal to 3. Okay, so What's its valence electron? The number of its valence electron. It's 3, right? 1 located at P subshell, and there are 2 located at the S shell. So it's valence 3, it's valence 2. Okay, for the silicon, N equals to 3, right? So 3 is the outer shell. Okay. So you have 2 electrons at S subshell, suborbital, and the 2 at P orbital. So total you have 4 valence. Okay. So for the magnesium, it has the 2 valence, and for the aluminum 3. For the silicon, you have 4 valence electron. Okay, you know what I'm saying? Okay. So this is the answer 2, 3, and 4. Okay, so the most element electron configuration are not stable, but well, some are stable, some not, because you're gonna influences by the environment surrounding atoms. Okay, so it might influences by its neighbors. Okay. Okay, so let's look like this. For the hydrogen and the helium, which one is stable? Which one is stable? Hydrogen and helium, which one is stable? I already have the answer here. Helium stable. Why? Why? Because as n equals to 1, right? N equals to 1. N equals to 1, right? We need 2 electrons to fulfill in s orbital, right? So for the hydrogen, in its s orbital, there are only 1 electron. You know what I'm saying? So look at this. For the hydrogen, for the s orbital, it only has 1 electron. We need a 2 to fulfill it, right? You know what I'm saying? And for the helium, we already have 2, so there's no any interact with the valence. Okay, I already occupied it, fully occupied it. But for the hydrogen, it still need 1 electron to stabilize it. Okay, let's look at the lithium. Okay, so the same is as n equals to 2. Its s orbital only has 1 electron, right? So we still need the other one to stabilize it. Normal sign. So you can look at this. Okay, so this is fulfilled. This is my stable. Well, it's my not stable. Well, it's P shell, right? It's P shell right here. Okay, and the boron maybe it's not stable. Okay, and because in the P shell we need 6, right, to fulfill the P orbital. And okay, so this is 6. So you already fulfill P orbital, and the 2 is to fulfill the S orbital. So it's stable. Okay, it's stable. And so on, and so on. Okay. So you will see what kind of elements are stable when its valence are fulfilled. Okay, for sodium, well, it's not fulfilled, right? We still need a 1. Okay, for the magnesium, it's more stable. Usually, okay, it's stable because we still have the sp3p and D, right? Okay. Okay, because n equals to 3, n equals to 3. And for the aluminum SP, okay, we need 6 to fulfill it, but only 1. Okay, for the argon, we fulfill the 6 in P, it's already fulfilled. Okay, so and so on, you will know as the valence shell usually are not fulfilled completely. So once the valence shell, the outer shell, not fulfilled completely, the element might not be stable. Okay, might not be stable. Okay, let's discuss about the electron activity. Okay, so if we need a stable element, its valence has to be 0. That means it is chemically unreactive or it is chemically inert. Okay. And the electron activity describes the tendency of atom to gain 1 electron to achieve 0 valence. Okay, gain 1 electron to achieve 0 valence. Okay, for example, such as the chloride are very electronegative because it has 7 electrons in its outer shell. So it's easy to react with the other one. It's easy to gain 1 electron. No, so chloride is very excited to get 1 electron to achieve 0 valence. Okay, okay. And the atoms with nearly empty outer shell has low electron negativities. So empty outer shell has a low electron activity. So its outer shell are empty. What's going to happen? Or you have the less electron. For example, its outer shell has only 1 electron. So it will tend to give up that 1 electron, right? It will give up that 1 electron, but it will not tend to receive other 7 electrons. Okay, you know what I'm saying? Okay. So let's look at this figure. It shows, okay, this N. Okay, let's look at this. This figure shows the electron activities corresponding to the position in the periodic table. So for the lithium, potassium, you have the the valence. Okay, 1 valence. Okay, for the calcium have 2 valence. For the magnesium have 2 valence, and so on. For the aluminum have 3 valence, and so on. Okay, so what that mean? That means we have the highest for the fluoride and chloride has the 7 valence. So for the higher valence, that means its electron activity is still high. Okay, you know what I'm saying? So when its valence achieve to 0, that's the inner, it's not gonna react with others because I already fulfilled with electron. I don't want to react with you. I don't want to give up my electron. I don't want to receive. I don't want to give up. Okay, I think already know this. So let's discuss about the periodic table. I think already you guys already be familiar with this periodic table. It contains information about each element and can identify useful trends in atomic size, reactivity, and the melting temperature, and so on. Okay, so you can look at this. So for the engineering point of view, for the mechanical or materials science engineer, what we are interested in? We are interested in, I already introduced those materials in our previous course. Okay, what's the polypolymer is? A polymer is consisting of carbon, right? Carbon. So you have to find the carbon in the specific group in the periodic table, right? And ceramics. Okay, so the combination of the element from group 1 to 5A is combined with oxygen, carbon, nitrogen, and so on. And for the metallic materials, the metals are group 1 and 2 and the transition metals. Okay, so if I give you a periodic table like this, so which region belongs to metal and metallic elements? You must know it, right? You have to quickly to draw. Okay, so probably this region. Okay, this region are metals. Okay, so you'll see the arrow, the blue arrows here, right? So the this arrow direction means the elements are easy to give up electron. Sorry, something wrong. For this direction, that means the elements are required to receive electron. Okay, to receive electron. So it has the higher electron activity. Okay, electron activity. So for the direction here, that means the electron positive. That means the elements are readily give up electron, to donate electron, to release electron. So for this periodic table, we need some concept. Which direction, which region, what's that mean? What's the materials tendency are located at different different place of this periodic table? Okay, so you must know, okay, right here is more electron positive, and right here, and right here is more electron negative, right? And the element between combined with this and this are ionic bonding, and the metals are right here, right? The metal or transition metal are here. Okay, so you need to have this concept to know, okay, which part of this periodic table provide the specific materials properties. Okay, I already mentioned this, right, during the previous slide. Okay, this direction or larger electron activity, that's mean it's easy to receive electron, and this direction means the smaller electron activity. That means the strong electropositivity. That means we are easy to release electron, to give up electron. So for your high school chemistry, you must learn it's called the redox reaction, right? Redox reaction, right? So which one? The electron activity, electron negative element or electron positive element is a good choice for the reducing agent. Okay, reducing, to reduce the metals. What's the characteristic of this reducing agent? it has to be readily to give up the electron, right? Because I give up an electron, some the ion, for example, the metal ion will receive the electron, and to reduce the metal atoms, Okay, so this region or compound are the good choice for reducing agent, to reduce metals or reduce something. Okay. Okay, so this course will be ended right here, and I will control my course, the recording within 1 hour. That's mean you just have to, watch the video within 1 hour to let you more concentrated on this course. Okay, so we see you next week, and I will finish the atomic bonding. Okay, at next week. Okay, so see you. Okay, today I'm gonna discuss about the bonding. Basically, there are 4 important mechanisms by atoms are bonded. Basically, there are metallic bonds, covalent bonds, ionic bonds, and the van der Waals bond. And the first 3 types are strong, and it's called primary bonds. And the van der Waals bonds are the secondary bonds, and it's weak. Okay, and it's weak. For the metallic bond, confer the properties of metals, including the good conductivity, because the electrons are not fixed in place. The electrons are freely moved. That means the numerous free electrons are on the surface of metal. Okay, metal. So you can see right here we have a metal iron core, and the electron cloud, or the valence electron is freely moved on the surface of metal. Okay, that's why it's highly conductive. It's very good conductive, and also metal has the good ductility. Okay, it's good conductivity. It's not brittle. It's ductile. Okay, it's not ductile. And metallic bonds are non-directional. Okay, non-directional. Basically, its physical properties are the same at any direction. And the metallic bonds has the property with high melting point. Okay, high melting point, and it has the electropositive characters, and is prone to corroded or oxidated. That's mean because the metal prefer to give up electron, right? It's preferred to give up electron. Okay. On the other hand, the metals is easy to corroded or oxidized, right? It's oxidized. And the second bond is called the covalent bond, and its characters are low conductive. Okay, because the valence are locked. Okay, the valence are locked. Okay, the valence are locked. For example, if we have a silicon atom, right? You have the four valence electron. Is that right? Okay, so here's the four electron. I have the 4 electron. You have the silicon. I have a 4 electron. right? Therefore, they were sharing electron between adjacent atoms. So they share electron, share electron, share electron. Also right here, just share electron. Right? So right here, share electron. It's covalent bonds. They share electron. Two atoms that are covalently bonded will each contribute at least one electron to the bond. And the shared electron might be considered to belong to both atoms. Well, so it's quite strong. Okay, it's quite strong. Okay. Covalent bond is similar, has the similar electron activity. They share, that's why I mentioned they share electron. And the bonds dominant by valence, and sp orbitals dominate bonding. One example is the methane. So carbon has 4 valence and 4 holes, right? They need 4 electrons to fill in its out orbital to become stable. And the hydrogen has one valence electron, as one valence electron. Okay, therefore the one valence electron for hydrogen will fill in the empty, the vacancy of the carbon's outer shell to form the covalent bond. Okay, covalent bonds right here. Okay. So the third bond is ionic bonds. Ionic bonds actually formed between materials with different activities. An ionic bond consists of the cation and the anion, which are formed after electron transfer. For example, the sodium chloride. We already knew it's salt, right? It's salt. You can buy it in supermarket. And for the sodium atoms, it has one valence. For the chloride atoms, it has one vacancy. You have seven valence, but one vacancy. So this valence electron from sodium will transfer to the chloride, right? After transfer, the sodium will become the anion and the chloride become the cation. And there's attraction force between them. Okay. Okay, so look, ionic bond basically, usually, but not always, usually consists of the metal and the non-metal, or we say the element prefer to donate electron, and the non-metal prefer to accept or receive electron, and they have the dissimilar electron activity. So one example is the magnesium oxide. Magnesium has the electron configuration here, and we always write down the form like we will modify this electron configuration to use the inner element. Okay, for the 1s2 and 2s2 and the 2sp6, it belongs to neon's electronic configuration. So we can write down it's the valence configuration. Okay, valence configuration. And the magnesium will transfer. Okay, we'll transfer 2 electrons to p orbital of oxygen, right? And there are 6 electrons to fulfill the p orbital, to fulfill the p orbital of the oxygen, right? So the magnesium will become positive, and the oxygen will become negative. Okay. Therefore, the ionic bond occur between the cation and the anion, and it requires electron transfer. And large difference in electron activities is required, like sodium chloride. Okay, sodium chloride. Okay, and the Coulombic attraction between these two ions. Okay, so let's look at the energy plot of the potential energy of the two ions. For example, we have the cation, we have the anions, and there's a distance between them, r, right here. So we can think of it's the boys and the girls. So what would you do when you see your boyfriend or girlfriend from the long distance? I think you guys must run together, right? You get closer and closer. You know what I'm saying? So when you see your boyfriend and the girlfriend, there's attraction between you, and both of you tend to get closer, right? Therefore, the distance r will getting smaller and smaller, right? So the attraction will dominate. Attraction will dominate the distance. Okay, so when you get closer to the certain distance right here, so the minimal energy achieved right here, right? Right here. It's called the bonding energy. This is called the bonding energy. So if you reach your girlfriend or boyfriend when you tighter, what's gonna happen? You might push it away, right? You might push it away. Therefore, the repulsion dominates. Okay, so the blue dot line represents the attraction, and the green dot line represents repulsion, and the red solid line represent the net energy. That means the combination of the repulsion energy and attraction energy. Okay, so the net energy equals to the attraction energy plus the repulsion energy can present like this. Okay, present like this, and A and B are constant. Okay. So I already mentioned this last week that the if the direction to the right side of the periodic table, it means it's more higher electron activity, right? So if the direction goes to the left of the periodic table, the element has the strong electron positivity. So this means that the element are located at this region. That means they are prefer to give up the electron, right? And the element located at the this region, that's mean okay, not including the inner gas, okay, right here, just right here. Okay. Okay, so they might as the okay, so between them, they have the huge difference of the electron activity. Therefore, they are easy to form the ceramics or ionic bonds Okay, and so on. And let's discuss about the secondary bond. The secondary bond, for example, like a hydrogen molecule. For one side with the positive charge and the other side with the negative charge. Okay. So the hydrogen molecules are bonded with a secondary bond. and it's fluctuated. It's fluctuated. It's fluctuated. Okay. And if the permanent secondary bond, or we can say the permanent dipole is a fluctuated dipole. Okay. And for the permanent dipole, for example, like the hydrogen chloride. The hydrogen chloride, the molecule is the positive side and negative side, right? Positive and negative. So the secondary bond or the Coulombic attraction between the hydrogen chloride's molecule. Okay. And for the polymer, consists of the covalent bond and the secondary bonds. So here is the carbon atom. Okay, and it's also the polymer chain. Okay, therefore the bonds between the carbon atom are dominated by covalent bonds, and the bonding between the polymer chain, this chain and this chain, are dominated by the secondary bond. Therefore, it mixes. The bonding of the polymer as mixing. Okay, it's mixing. Therefore, we have a briefly summary is that the ionic bonds. Okay, the ionic bonds. Its bonding energy is huge and it's non-directional, and most of these ceramics are dominated by ionic bond. And the covalent bond, it's the bonding energy is variable. For example, diamond has very high bonding energy. Okay, high bonding energy. And for the polymer chain, its covalent bond is weak. Okay, it's weak. Okay, it's weak. And the metallic bond, its bonding energy is also variable. For example, the tungsten has the extremely high melting temperature, right? That means it has very high bonding energy. Okay, and also like mercury, its metallic bond is quite weak. Okay, it's quite weak. Okay, it's quite weak. Okay, and the secondary bond, its bonding energy is smallest, it's directional. Okay, and it's the inner chain, inner polymer chain, or inner molecular. Okay, its bonding force is low and it's directional. I will explain why it is directional later. Okay, so let's look at the this bonding energy plot. So, for example, we have two types of materials with two different bonding energy. Right here, one, and right here, bonding energy 2. So 1 and 2, materials 1 and 2, which one has the higher melting temperature? From this plot, we can tell for the materials 1, we have the larger melting temperature, right? Because we need higher potential, or higher external potential to break up those atoms, right? To break up those atoms. Okay. And if we look at the CTE, it's called the coefficient of thermal expansion, CTE. Okay, so for most of the materials, okay, for most of materials, when we heat it, its volume will expand it, right? Will expand it, usually, okay, for most, but not all, for most of the materials. So let's say if we have two type of materials, 1 and 2. So if the materials has the higher bonding energy, I mean the value of bonding energy, okay, the value, higher value of the bonding energy. That means its volume or its dimension is not easy to change when we heat it up. Okay, when we accept, when we observe the thermal energy, its dimension will remain. But if its bonding energy is small, bonding energy is small, when we heat up, its dimension or volume will change a lot. Okay, so you can see the bonding energy is related to its melting temperature and the coefficient of thermal expansion. Okay, so I provide you guys some summary right here. So ceramics consists of the ionic bond and the covalent bond or mixed bond of ionic and covalent bond. Okay, its bonding energy is large, and you have the large bonding energy. Of course, therefore you have the large melting temperature, and with a small CTE. And for the metallic bond, its bonding energy is variable. So you have the moderate melting temperature and the bonding energy and the CTE. Okay, for polymer, it's also mixed bond. The mixed bond is covalent and the secondary. Okay, and it has the directional property. So what's that mean? For example, if I apply a force this direction, it's x direction, F, and I apply force this direction, it's y direction. Okay, so which direction is easy to make the polymer fail? X or Y? Of course, Y direction is weaker than X direction, right? Because because we have the covalent bond here, right, between the carbon atoms, right? Covalent bond is stronger than secondary bonds. Okay, so if we apply the force along the Y direction, it's gonna be peel off or delaminate or fail or fracture, right? If we apply the force along the X direction, because the covalent bond existed and a covalent bond and secondary bond are coexistent. Therefore, the strands along the X direction is much stronger than that in Y direction. Okay. Okay, so for the secondary bond dominated, you have the small melting temperature and bonding energy and large CTE. Its dimension is highly dependent on temperature. Okay, it's very sensitive to temperature. Okay, its dimension is highly dependent on temperature. Okay, so our course will be ended here. So if you guys have any questions, yeah, please just leave your message to me, and we'll meet next week. Thank you.